Hello, everybody. This is Carol speaking. Welcome to a new series of PolyWorks webinar, and we'll get right down to it. Today, we are covering hints for inspecting thin parts efficiently. And let's welcome back our very own John Sebastian Blais, as he is our presenter today. John Sebastian is a member of the technical support group. And we have kept the same format, so if you have any questions during the webinar, please use the questions panel, and I will be monitoring the questions throughout the webinar. We will have a short Q&A session at the end. If we don't have time to answer all of the questions, we will get back to you by email. And yes, we are still recording this webinar, so it will be available for later viewing. John Sebastian, it's all yours.
Thanks, Carol. Today, as the title suggests, I would like to provide helpful hints that you can use while inspecting thin parts. Now, those thin parts can be made out of sheet metal, out of plastic, or composite material. Those tips will apply to all of those thin parts. And let's get started immediately. And the first item I would like to highlight is you could actually enable a special application mode that we called sheet metal. Now, as you can tell, this is probably related to thin parts. And what it will do is it will preset certain parameters in PolyWorks Inspector that are different than the default parameters that you're getting when you're using the manufacturing application mode. So let's get started. So instead of explaining all of those changes one at a time, what I'm going to do is start an inspection project and highlight those changes as we're going through it. So this first inspection will be done solely by using probing. So right now, I want to show you the content of this project. I've already imported a CAD model. I did perform a surface point pre-alignment by probing, and you can already see that big ghost yellowish part. That's actually the scans that I've made because I'm about to do the probing using our virtual probe. So I'm going to probe that fake data, if you want, that's over there. And let me just show you the setup that corresponds to what you see in yellow. So I want to draw your attention on the fact that this part has a large flat portion that is currently being pressed against the granite surface. Now, this is going to be key later, but this is a thin part made out of sheet metal that we'd like to inspect by probing. So let's get started immediately by concentrating on curve-based features or holes that you would like to probe on the part. First of all, like this slot here, if I create this slot feature, I just want to draw your attention on the fact that if I launch probing of any curve-based feature, one of the change you will notice is the fact that the thin material parameter is enabled by default. Now, let me just change a couple of other parameters where I'm going to probe this slot with sides and arc. And let's take a look at what's going to happen when I use the thin material mode. And of course, when I do, I want to make sure I use the appropriate thickness, which I forgot to provide when, so I'm just going to stop probing for now, launch it again. And it's important to provide the material thickness approximately to go with the thin material. So let me hide the CAD to make sure I probe the appropriate section. So let's go with the constraining plane. And what the thin material will do is sometimes it's very hard to press the probe against the sidewall of the sheet metal part. Now this one is pretty thick, so I'm able to do it. But when you have a very thin part, this might be more of a challenge. So what would happen is your probe could easily slip. If that happens, you can hear that the probe point is not accepted. I'll explain in a second in detail what's going to happen with this, because there's more to it than just rejecting points. So let me just finish with the final art that we have here. And I just want to highlight the result, and you can see it overlaps the scan data very well. Now let me just toggle back to the PowerPoint presentation, just so you can see with those graphics what actually happens when you're using the thin material mode. First of all, you probe your constraining plane. And with the thickness you're actually providing, we're defining a zone that you see in purple right now. Now, whenever you're probing a curve-based feature, there can be three different situations where your probe is located. Normally, if you're able to hold the probe against the sidewall surface, the center point of the probe is right in that zone. And that means the point is accepted and compensated to a distance that corresponds to the probe radius that we see with the arrow there. Now, the second possibility is the fact that the probe could slip and you could be totally away from the constraining plane or the zone, and the point will be rejected. But what's really interesting is when it's very hard to hold the probe against the sidewall surface, you might be contacting the corner. In that case, the center point of your probe is still within a probe radius of that zone. And what happens in this case is the point is still accepted. However, it's going to be compensated by a distance that is slightly smaller than the radius of the probe tip. So this is a geometric calculation that we're making, and that happens in the background without you noticing. Now, what's the advantage of that? Well, it means that you can probe any thickness of sheet metal with pretty much any size of probe tip, that as long as it matches the hole and you can enter in it. So as long as the tip is in contact with the corner, you're going to be okay. And one tip or hint I can give you to measure accurately holes this way is if you can afford to have a metallic ruler or something flat that you can put underneath the hole, your probe could actually rest against that surface to actually perform the measurement. Now, here's an example. If I look at this part, there's a hole here that was standing against the granite surface, and this hole would be extremely easy to probe because I can push and contact the granite as well as the corner of the curve-based feature at the same time. So let me just jump to another hole that I will concentrate on to give you another hint. So this is the hole that we have here at the front, and you can see the CAD only shows a clearance hole, but if I show you this picture, the part actually has a threaded insert that was welded to it, or weld nut if you want. Now, of course, I could measure the clearance hole on the sheet metal, but I have no guarantee that this clearance hole is centered on the threaded insert that was welded. So in that case, we might be more interested in measuring the threaded hole rather than the clearance hole. And in order to do that, I mean, it could be very hard to use a probe to obtain a good diameter on those threads. So my tip to you would be to use a gauge pin or to put a stud with the same thread into the weld nut. In that case, you can create the features that you need. So let's say I go with the constraining plane, the circle itself, and when it's time to probe this, let me just show you what you can do. So first of all, rather than using the standard method, you will be interested in knowing that there's a method that's called pin and hole. So whenever you have that, of course, the thin material option that was there a little while ago in the standard mode is no longer there because obviously this has nothing to do with thin material. In this case, what I'm going to do is specify that I want to use an explicit plane. That's going to be plane 1. So I'm going to go ahead and probe this. Allow me just to hide the CAD again, and I will also make the plane disappear so it's not in my way as I'm measuring. So I'm measuring the constraining plane right now. And now I'm going to measure, as a second step, the circle itself by probing the pin cylinder. So in other words, it's an easy way to probe a circle without having to do any constructions that imply a cylinder, simply because the circle probing method called pin and hole includes that cylinder. And I just want to draw your attention, if I zoom in a little bit, we can see that hole that has been created. Now, of course, the two don't have the same diameter, so maybe I would like to get rid of that diameter control, and I'd rather use maybe a position control with respect, let's say, to a primary datum plane that would be the plane that rests against the surface, the plane that we probe here on the side, so allow me just to access its properties and say this is datum B. and also our slot here, which would be my tertiary datum, datum C. Now, this actually highlights another issue that I would like to provide a hint for. How do you measure a plane, like in this case, datum plane A, that rests against the table's surface? Some of you might be thinking, let's do a second device position, let's move the part, but if I do that, the part will be deformed by the fact it's no longer pressed against the granite table. So I'd like to share a trick where you can actually measure a plane that would be hidden or unreachable. So in that case, I'm going to start by creating a plane directly from the CAD model. And let me just explain what I'm about to do. So I will hide the CAD model again and change the rendering of my plane to better understand what I'm about to do. So I'm going to go and look at it as a flat rendering. What I want to draw your attention to is the fact that this is light blue. This is the positive side of that plane, and the dark blue we're seeing here is actually inside the material, so the negative side of that plane. The table surface would be actually inverted from that orientation. So allow me to invert that, and I will rename that plane table plane. There you go. So this would correspond to a plane I can measure by probing the surface of the table. Now, how do I derive my datum plane A from this? Well, this is the hint I want to give you. So what I will do is create a dependent plane feature from that plane. So I'm going to go from object, and the plane I'm going to use is, or the method I'm going to use is planes and offset. Now, normally this technique is used to create parallel planes at a given offset from each other. In this case, because the two planes are exactly mating to one to another, I'm going to leave the offset at 0, and that will be my datum plane A. Now, allow me just to hide the table plane, change the rendering of this, and I'm also going to change the color of that plane. Right now, it faces the same direction as the table plane, so what I'm about to do is simply invert that orientation, so I'm back with the original plane that corresponds to the face that's on the CAD model. However, the big difference is this plane is a dependent feature that will be immediately measured as soon as the table plane is being measured. So let me just show you that. If I probe the table plane, I can just probe those points. And as soon as this is done, then datum plane A has its measured primitive, which means that I can now go back to my circle, create the appropriate position control by using datum plane A, B, and C. And on top of that, I'll get my measurement. And on top of that, I can also perform a datum reference frame alignment that would use that datum plane A. So this is, let's say, the entire content of the project when it comes to probing. And let's say I would like to repeat that inspection. Of course, I'm going to create a piece template that I will call probing. So I know that this piece template can be used for re-inspecting this piece by probing. Now, what I'm about to do is continue my series of hints by showing you what the sheet metal application mode does for scanning. So what I would like is to create another inspection project where I'm only going to change the measurement method from what we've done so far by probing. So in this case, I'm going to create a new piece. So I'm simply going to run the current template I have, but when I'm going to be asked for probing, this is where I'm going to start scanning. We can do modifications like that. Now, because this is a webinar and right now the part is still inside the fixture, I wouldn't want to have to reprobe the surface point alignment. So I'm going to say it's a fixed alignment setup, so I'm not being prompted to remeasure the surface point alignment. So I'm going to go create, and oh, I forgot to do a little thing. Allow me to go back to my template for a second. just so you know, the surface scans wouldn't be present in this template because I use them just to do the virtual probing. But right now, what I would like to do is reprobe this. Normally, I don't need to have those scans in there. So let me go ahead and launch the new piece again. I'm going to say use the fixed alignment setup, and we're all set. So as you can see, I'm not being prompted for measuring the surface point alignment. However, I'm now asked to probe datum slot C. So let me stop that. And instead, I'm going to start scanning. Now, the second thing the sheet metal application mode will change in terms of default parameters is the scan type you're going to be using whenever you start one of the laser scanning plugin. Rather than just capturing surface scans, you're going to be prompted for surface and boundary scanning. So I'm going to leave this way and just use the line scan player to capture the data I need. So as you can see, the surface scan's being captured, and there's also boundary data that is created. So I'm just going to close this to finalize the mesh. And to accompany this boundary scanning, let me just show you, if I extract all my features, you're going to see that my slot has been extracted. And if I show you the data points that were selected, you can clearly see that the slot or the curve-based feature has used the boundary data to fit itself. So this is because it's actually the third change you're going to see when it comes to using the sheet metal application mode. By default, the extraction method for measuring over scan data will use the trimmed submethod and will consider boundary data. Of course, surface data will still be considered for the constraining plane. So this will minimize the number of changes you have to do whenever you're extracting curve-based features on thin parts. Now, let me draw your attention. We can see the alignment is slightly different there. So let me focus your attention on different items that we've measured so we identify the source of that deviation. First of all, if I look at the circle here and select the measured data points, we can see that we have boundary data over there, but that's not reliable data I want to use. And in that case, probably I want to change the default extraction parameters and maybe return to considering surface data for this one. And rather than a trimmed hole, I would like to use the standard method that expects to use some sidewall data to fit the circle. But if I do this, and in fact, let me just also make sure I have the proper constraining plane. If I do this, you're going to see I have a warning that tells me that after making those changes, it couldn't find any data suited for that circle. So in that case, I need to figure out what I could do. And this is something, again, I can give you as a tip. As you can see, there are no method called pin and hole for the extraction, but you can still tune the parameters to do that. So in order to do it, let me just show you the parameters. Normally, we're expecting to have sidewall data inside the hole below the constraining plane. Let me just show you with the offset method that we could actually use an offset value that would move that zone deeper into the hole. I'm going to use that to actually invert the location of the zone. Rather than using a positive offset to plane value, I'm going to go 15 millimeters higher than the constraining plane. And this would allow me to define a zone that will capture the point on that stud or on the gauge pin that you have inserted. Now I'm going 15 millimeters above the constraining plane, which means I can reach a height of 14 millimeters of data. And if I do that, the other thing you need to know is about the max angle filtering. Because that surface data is actually an external feature and that hole is an internal feature, I cannot filter using the max angle, so I'm going to disable it. Now that I've done this, let me just rotate so you see better the circle that we've obtained. It's over there. And if I select the scan data that was used, you can see that we've used 15 millimeters of that stud to actually fit that circle. And then finally, I'm going to try to investigate why I'm having such a wrong alignment. Well, in this case, you can see our datum plane A, which seems to be on top of the part. And why exactly is that so? If I select the measured data points that are associated with the table plane, you can see that the part, or the flat surface that was on top of the part and not the surface that's in contact with the table, has been selected. How can I prevent that from happening? Well, I can actually crop the nominal plane that was defined exactly where the CAD is to actually cover the area defined where the table is. So I can change the contour of that plane, and that means that the extraction will now correct itself. And if you can see right now, if I go, select measured data points, these are the points that were selected for the extraction, and this is how datum plane A was derived. And you can see now the alignment is much closer than what we expected because of that. So right now, at this point, I could choose to save this as a piece template that I would call scanning, which means that right now, every time I'm starting a new piece, I can choose between probing or scanning. And if, in conclusion, I summarize what I went through, I just demonstrated that the sheet metal application has three important effects. First of all, it enables a thin material option for probing curve-based features. Second, it enables surface and boundary scanning by default. And it enables extractions of curve-based features to consider boundary data with the trim submethod. And all these should increase the efficiency with which you inspect thin parts. In addition, I just gave you 2 hints on how to measure threaded holes and unreachable planes that can be used with basically any type of parts.
Thank you, John Sebastian. We do have some questions that are coming in. So the first one, if I put a new part in, so a new part in the fixture, how do I remeasure the surface point alignment instead of using the fixed setup that you currently have?
Oh, good question. Yes, I use the fixed alignment setup to avoid having to reprobe the surface point alignment in my scanning example. However, right now, if I go and choose that scanning template to repeat a new piece, if you expand the fixed alignment setup at any time, no matter which project or which piece you're using, you can always disable or uncheck the fixed alignment setup. And what would happen in this case is as soon as you press the new piece, then I'd be prompted for measuring that surface point alignment. Good question.
Second question. It's related to the thin material probing option that we saw earlier. Would it also be working on the opposite side of the sheet metal instead of how you showed it on the top?
Oh, yes, of course. The graphics I've used to explain the thin material, the 3 scenarios I gave, the probe was only on top, on the side where the constraining plane was, but the same thing would happen if you were on the lower edge of the curve-based feature or on the hole. So the zone itself applies symmetrically on both sides.
Thank you. And it's all the time that we have for the questions right now. There's a few more that are coming in, and we will get back to you by email. So this webinar has been recorded. It will be available on the Innovmetrics software website. Navigate to the support section. It will also be available on the Innovmetrics software channel on YouTube. And it's this time of the year again, so a reminder that we hope to see you at the PolyWorks Conference USA 2019 in Novi, Michigan, on April 24th and 25th. The 2-day event brings the PolyWorks community together for 3 PolyWorks 2019 launch presentations with embedded workshops, PolyWorks success stories by experienced users, and opportunities to grow your network and strengthen your PolyWorks skills. And of course, more. We keep a few surprises, of course. And register today at the early bird rate, yes, which expires March 1st. So for more information, visit our website at innovmetrics.com. And our next webinar will be about inspecting bent tubes and rods. It is scheduled for March 14, 2019. Thank you for joining us this morning. It was a great crowd. Thank you for being back with us, and we'll see you next time. Bye-bye, everybody.